All right.
I wasn't there. So.
I just handed back some homework, and you're about ready to hand me some. The last assignment of the semester, right?
We haven't finished it yet, though.
You're right. There's one. The last question I had not on mathematical induction. I have not shown you how to do that yet. So I'm gonna present that material in a minute. But before we do that, let's see if there's any questions about all the other exercises that you had to do. Question.
Is 11.7.2 really one step?
It could be. I think it might. I thought it was like 2 or 3, but the question is about 11.72. 1172. Here, let's take a look at 1172. It's this S is a subset of the power set of S. I think there's only one thing to do, right? You just got to go back to the definition of the power set of S, and once you do that, then you'll see.
Yeah, but I don't get. Do you have to do the whole V as an element of the power set?
No. I think you go.
V is an element of the power set. The V is a set. The V variable is a set variable.
No. But this is a Boolean expression. We're not the way. Okay, hold on. Listen, there's a principle here. When the time that you use the technique, let V be an arbitrary element and show that V is an element of S equals V is an element of T. That is a technique for proving that two sets are equal. To prove 11.72 is not a statement that two sets are equal. So therefore, you don't use that technique. Are you with me on that?
Yeah.
Okay.
He's talking about 11.23 because it says V is an element of the power set of S, but V is a set.
Wait. 11.23?
He's talking about type conflict, possibly. It actually does.
Like in proving 1172.
The theorem, the definition of a power set is 11.23.
Yeah, right. It's 11.23.
So you have V is an element.
So you have.
Except that V is a set variable.
It is.
Because it's, or else you'd have type conflict.
But this is like a one-stepper.
Yeah, exactly.
That's what we're asking.
Yeah.
So, yeah. Because V is a set.
But I mean, if you just go do look 11.23, you can substitute equals for equals, right? This is an element of this equals this, or this equals this. Are you with me?
Yeah, which is.
I mean, you can substitute equals for equals, right?
There's probably even a theorem about that. S is a subset of S.
Yeah.
Okay, are we good?
Yeah.
Yes. Question? Another question? Or we're all good?
So we're good.
You're saying we're all good. Any other question? Anybody else? Are we all okay? Shall we go on to chapter 12? All right. Now, okay. So, here are the theorems for chapter 12. Chapter 12 the topic is mathematical induction. Now, let me say that this is going to be a proof technique. And let me say that this proof by mathematical induction is probably the most important proof technique in all of computer science. It probably is. I mean, we will use proof by mathematical induction throughout the rest of the major, the courses in the major. As cameraman can attest, he's back there saying an amen. He's back there saying an amen, brother. Okay? So now, here is our first. Now, this is a lot of theory here. Axiom, mathematical induction over M for all, nested for all implies blah, 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 mathematical induction over N, mathematical induction over. So this is, and we're going to go through this, but I think before we do that, I think it's best that we do a specific example so that we can see all of this in the context of this example. So what I'm going to do is I'm going to do an example, and this example will be a proof by mathematical induction, and as all you have to do is follow the steps that we do here in order to in order to do the homework, the one homework problem that's due today. All right? And I think by the time we get finished with this, you'll be able, you'll just be, and I'll give you some time. We might have to skip this in the video. But then, or we can end early or something, and I'll give you some time and you can do it. But if you just, it's very straightforward, but, and so here's how it works. What we're going to do is, in the book, there is an equation 12.1, all right? And 12.1 in the book is the following, okay? Now, we're going to call 12.1 P dot N, all right? And P stands for predicate. In other words, it's something that's either true or false, right? Okay. So P dot N is the following expression. Now check this out. Sum on I, range 1 less than or equal to I less than N, body 2 times I minus 1, close paren, equals N squared.
What does the P dot N mean?
The P dot N is this whole thing. Okay, so here, let me ask you a question. Okay, hold on. I'm going to answer your question. Okay, so now, is this I bound or free? It's bound to this I, right? Is this N bound or free? It's free. Is this N the same as this N? Is this N the same as this N?
No. Maybe. Well, in the alphabet, yeah.
Well, I know, but is this N bound or free? It's free. That means if you were to expand this whole thing out, there would be some N's in it. Are you with me? And we're saying that whatever this is, that equals this N squared, right? So this N is the same as this N. Are you with me on this? Are you with me? So now, this is claiming, so this P dot N, so this whole expression has an N in it. That's why we say P dot N, because there is an N in this whole thing. Are you with me? For example, let's just write down P dot 1. All right, let's just expand it out and let's just write down P dot 1. Okay? Kale, what do you think if I were to expand this out and had N be 1? What would we have on the left-hand side here? Well, this would be the sum on I, 1 less than or equal to I, less than 1? No, sorry. This is less than or equal to. Sorry, my mistake. So this is 1 less than or equal to I, less than or equal to 1. So what possible values of I would we have here? Hold on.
1.
Yeah, so there's one value, and that value is 1. Okay, so what would this be?
2 times 1 minus 1.
Okay, so this would be 2 times 1 minus 1, and this would equal what?
1 squared.
1 squared. Now, does everybody see how we expanded that out?
Yeah.
Is this true?
Yeah.
Yeah, because
What's the theorem?
what is this? This is like 1 equals 1 squared, right? Actually, here, let's write it like this. Let's do the math in our head here. Let's just say that this is 1 equals 1 squared. Now, what is P dot 2? So actually, if you were to expand this out, what would, now if P dot N, we're saying P dot 2. So in this case, we're doing P dot 2. So what would that be? 1 less than or equal to I less than or equal to 2. So what would the numbers for I be? 1 and 2. So what would this be if they were 1 and 2?
2 times 1 minus 1.
Which is 1,
And 2 times 2 minus 1.
which is, and then what about those? And what is this operation? Add them. So what are we saying? 1. 1 plus 3. Okay, and now what would you have here? 2 squared, and this is 2 squared. Is that true? Okay, Rochelle, what would happen if we did P dot 3? This would be what? So what would the values of I be? 1, 2, and 3. And so this would be what?
1 plus 3 plus
And then what?
5.
Yes. So this would be 1 plus 3 plus 5. And then what would this be?
5 squared. Or sorry, 3 squared.
Yeah, 3 squared. Is everybody clear on this? Is that true? 1 plus 3 is 4, plus 5 is 9. 3 squared is 9. Do we need to do another one? P dot 4 is what? 1 plus 3 plus 5 plus 7 is what? 4 squared. Is that true? Did you guys realize that if you added up odd numbers, you get a square?
Well, I do now.
Pretty interesting, huh? This is true. Are you with me? This is true. This is true. This is true. Do you think it's true for, do you think 1 plus 3 plus 5 plus 7 plus 9 is 25?
Yeah, I know it.
Do you think that it's true, do you think that P dot n is true for an infinite number, for all
For all n.
n? Do you think it's true for all of them?
For all n type n.
Do you think it's true? My question is, do you think it's true?
It says so right there.
Well, no. What I'm asking is, but how can we prove it? We can't do proof by example. I mean, the only way. Can we do proof by example? I mean, should we do it for? But if we did it for 9, 11, 13, blah 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 blah. I mean, you'd have to. If you did it, how can we prove it that it's true for an infinite number of n? I mean, wouldn't we have to do like an infinite number? We'd have to work this out an infinite number of times. Are you with me? Does everybody see what the problem is? The problem is we want to prove this is true for an infinite number of n's, yeah? For all n. But we don't have time to show it, or we don't have the space either. We don't have the room on the board, and we don't have the time to do an infinite number, right? Because no matter which bigger one we get, you say, oh, it might not be true for the next one. Are you with me? So we'd have to do it for the next. Oh, how do you know it's true? Well, we did it all the way up here. Well, it might not be true for the next one. So, how do you do that? So here's the question. How can we prove P dot n? How can we prove P dot n is true, P dot n true for all n greater than or equal to 1. Not just, what did we do here? Not just 1 less than or equal to n less than or equal to 4. How can we do that? Does everybody see that that's our problem? That is our problem. How can we do that? Well, the way we do this is by this technique called mathematical induction. And it's based on the following idea. Let's go over here. Idea. Here's the idea. Now, watch this. Suppose that we could prove the following. Suppose we could prove that P dot n implies P of n plus 1 in general. Do you see what I mean? In other words, we're not going to prove P1 and then P2 and then P3 and then P4. We're going to prove, what we're going to do is we're going to prove that if P dot, if you went dot dot dot, we're going to prove that if P dot n is true, then P dot n plus 1 is true. Are you with me? If we could do this in general, then we could use 3.77. Do you remember modus ponens? Remember modus ponens?
No.
Remember the name maybe?
P implies Q implies Q.
What is modus ponens? P,
and
P,
implies Q
yeah,
implies
P and P implies Q implies Q. Does that looks familiar, right? If you go look it up, right? Yeah, we had a modus tollens too. Remember that?
No.
It was the negative. Yeah, we didn't use, we never used. Well, anyway, it's in there. And if you look up 377, this is what 377 says. And does this make sense? Because what is this saying? P and if P then Q. I mean, because suppose you know that P is true, and you also know that if P then Q is true. Well, then you know that Q is true, right? Does that make sense? And it's a theorem, and you know we can look at. Okay, so we could use modus ponens as follows. Okay, here's how we're going to use it. Okay, first of all, what we're going to do is we're going to now let's suppose that we've done this already. All right, let's suppose that we've proved that P dot n implies P dot n plus 1. All right, then here's what we would do. First, we would prove P dot 1. First, prove P dot 1. Okay, this is called the base case. Called the base case. All right. Okay, then that's the first part. Okay, then what happens is we do this. Now watch this. So we've proved P dot 1, right? But if we did this in general, what do we know? If we did this in general, then we know that P dot 1 implies P dot 2, right? Okay, so then we have this. We have we proved P dot 1, but we also know that P dot 1 implies P dot 2, right? So that implies what?
That implies a P dot 2.
This implies P dot 2. Are you right? So now we have P dot 2.
All the way down the chain.
Yeah, all the way down. And so now, but then we have P dot 2, but we also know, if we did this in general, we know specifically that what? P dot what?
P dot 2.
P dot 2,
And P dot 2 implies P dot 3.
and P dot 2 implies P dot 3. Well, that must imply what? P dot 3. So now we got P dot 3, right? And then P dot 3, et cetera, et cetera. So P dot 3 and P dot 3 implies P dot 4, but that implies that we've got P dot 4. And so obviously you can just this, you know, this if you can do this in general, if you can start with the first one, and then if you can do this one in general, then ... And the conclusion is that P dot n is true for all n greater than or equal to 1. So conclusion is that P dot n is true for all n greater than or equal to 1, because we proved it for 1, and then we proved it in general that if it's true for n, it must be true for n plus 1. So if it's true for 1, it's got to be true for 2. But if it's true for 2, it's got to be true for 3. It's got to be true for 4, blah, 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 right? Okay, so proving P dot 1 is called the base case. So proving P dot 1 is called the base case. And proving that P dot n implies P dot n plus 1, or P of n plus 1, is called the induction case. All right? So anytime you have a proof by mathematical induction, you have to write down two subproofs. You have to write down two things. You have to write down P dot 1, or you have to write down the base case, and then you have to write down, and you got to prove the base case, and then you got to prove the induction case, and then by this reasoning, by mathematical induction, you've proved it for all. Okay? So now here is the, and here again I'm going to be very picky about how to do the format. Yeah, you're not going to like this. Okay. Okay, so here we go. Because I'm going to insist on a certain format. And I'm going to insist that you write, I'm going to actually insist that you write down a sentence in English, which you will rebel at. Okay, so here's... Well, you guys that hate writing sentences in English, you like writing statements in predicate and propositional calculus, and I would like German. Okay, so here's our example. Let's prove here. So here it is. Let's do this example. Let's prove sum on I 1 less than or equal to I less than or equal to n body 2 times I minus 1 equals n squared. Okay? This is what the one that we started with, all right?
12.1.
And and here is the format that you have to do. So first you have to write base case. Okay? First you have to write the base case. And what you do is, this is what we're trying to prove, right? This is the thing that we're trying to prove, right? So let's write it down. So we'll start with this whole thing. So we'll go sum on I 1 less than or equal to I less than or equal to n body 2 times I minus 1 equals n squared. All right, so this is what we're trying to prove. And we say equals, and now we invoke the base case. Now, here's the thing about the base case. In this particular example, the base case is the first one, right? Now, sometimes it's 1, sometimes it's 0, sometimes it's 2. I mean, the way you tell which one is the base case is it's the first one that I can be. Are you with me? So in this case, in this example, the base case is 1, but it might not be 1. It could be 0. It depends. So you see it from here. So here what we say base case n equals 1. Are you with me? All right? And then we just bring this down, and everywhere there's an n, we put a 1, right? So this is sum on I 1 less than or equal to I less than or equal to 1 body 2 times I minus 1 equals 1 squared. Is everybody good?
So isn't the first number n can be then?
It's the first number. It's the lowest number. Oh, here. Hold on. Yeah. Hold on. I forgot. Yeah, my mistake. No. Yeah. Hold on. My mistake. I forgot. I left something out here. We want to prove that this is true for all n greater than or equal to 1. So that has to be in the problem statement. Actually, that wasn't quite accurate when I said the way you tell what the base case is by looking at this. That has to be given as part of the problem. The values of n that you're trying to prove it for has to be given as part of the problem. Are you with me? So because this is for all n greater than or equal to 1, that's what makes the base case be 1. Are you with me? And if they don't give this to you, then you need to ask. Like if I ever mistakenly give you a homework assignment, or there's a question on the exam, and I say, wait, for what values of n? Well, that's got to be given. And so the base case is the first one. Yeah?
Yeah.
Now, so this equals, by math, we're just going to invoke some math here, right? So tell me, so what are the possible values of I here? 1. Yeah, so I is 1. So this whole thing is what? 2 times 1 minus 1. So this is 2 times 1 minus 1 equals, and what's 1 squared? 1. And what's 2 times 1 minus 1? 1. So this is 1 equals 1. Right? And we're done. Boom. Because we know that that's true. Right? Well, we're done with the base. We are done with the base case. Now, does everybody see how we
Can we
do?
do 2 steps of math, or can we just?
Yeah, you can do 2 steps with math and do 1 equals 1 if you want. But this you have to do. You need to say what you need to quote the base. You need to invoke the base case here. Are you with me? You need to invoke the base case, right? All right. Now, you guys, here's where I'm going to be a real stickler. Okay? This is the induction case. All right? And here I insist that you write down the following sentence. I insist. What you must do is you must state what it is that you are trying to prove using what as the inductive hypothesis. So here's what we need to do. Now remember what we said that the key to the induction step was? If we can prove that P dot n does what? Implies P dot n plus 1. So, and guess what technique we're always going to use? You know, here, this little scratch paper. We want to show P dot n implies P n plus 1. Now what's the most common, what's a very common proof technique that we've used to do this? Assume the conjuncts of the antecedent. So what we're going to do, and we will always do that. Yeah, okay. So and we're always going to do that. So what we'll always do is we'll always prove this, assuming this, and this is going to be called the inductive hypothesis, right? So we're going to prove this, assuming this, okay? So, and that's always the way that we'll do it. That's always the way we'll do it, by assuming the conjuncts of the antecedent. There's only one antecedent here, all right? Okay, so here we go. So what must we prove? Now, tell me, let's come over here to this side. What is it that we want to prove? And using what? Remember, we said we want to prove P dot n implies P of n plus 1. So we will prove what, assuming what? So tell me, if this is what our P dot n is, then what do we have to prove? Well, then what is this with n plus 1? What is it? It's what? Sum on I, 1 less than or equal to n plus 1. Body 2 times I minus 1 equals what? N plus 1 squared. Are you with me? Okay, so I insist that you write that out. We must prove sum on I, range 1 less than or equal to I less than or equal to what? N plus 1, body what? 2 times I minus 1 equals what? N plus 1 squared. Are you with me?
Wait. Then you have to write out what?
Yeah, and now, yeah, we're not finished yet. Using, okay, so now using over here, so we're going to prove this using what as the inductive hypothesis? Yeah, and I insist that you write it out again. You're not going to like it, but I insist that you write it out. Using sum on I, 1 less than or equal to I less than or equal to what? N, body what? 2 times I minus 1 equals what? N squared as the what? What is this called? As the what? No, not the base case. The base case is the case n equals 1. But what is this called? This is not called the base case. What is this called? As the inductive. It's not the same thing as the inductive hypothesis. This sentence is key. And it's mandatory that you write this sentence out or you won't get full credit. All right? This sentence is key. And even though you're saying, well, I'm just rewriting what it is we're trying to prove, blah, blah, I don't care. You have to rewrite.
Can we, instead of writing it like that, can we just write using the second quantification with the equals implies the first quantification?
No. Here's why. I want you to do it this way, because here's why. Because when you invoke in the proof, you're going to invoke the inductive hypothesis, and I want to see.
Can't you write that implies the one above it?
I know what you're saying. No. What I'm saying is I want you to use the word inductive hypothesis here, because in the proof we're going to invoke the inductive hypothesis, and we need to see what the inductive hypothesis is up here. Are you with me? I'm a stickler, but this is a dictatorship, not a democracy. See how? Sorry. Okay, anyway. Yeah, cut that. Okay, so now tell me what it is all right, so now look, you guys, tell me what is it that we are trying to prove? What is it we have to prove? We got to prove this up here, right? Now, do you think we should start, this is an equals, right? Do you think we should start with the left-hand side and get it to equal the right-hand side, or should we start with the right-hand side and get it to equal the left-hand side?
Left-hand side.
I think we should start with the left-hand side because this is the more complicated one. Are you with me? Is everybody clear?
Yeah.
So here's what we do. We start with the left-hand side. So we do this. Sum on I. 1 less than or equal to I less than or equal to n plus 1 body 2 times I minus 1 equals. Is everybody clear of what we're starting with here?
Yes.
Equals. Now, you guys, what do we have here? We have 1 less than or equal to I less than or equal to n plus 1. But what are we going to have to work with? We have this. So what should we do? Split off term is right. Okay? So this equals by, and so who wants to split off the term? You remember how split off term works? Split off term. Now remember when we did those exercises for split off term? So what do you think, Ben? What is the last, and we're not going to split off the first term, we're going to split off the last term, right?
Okay.
So it would be what?
Sum over I.
Sum over I.
1 is less than or equal to I is less than or equal to n.
Yes.
Body 2 times I minus 1.
Body 2 times I minus 1. Now, what operator goes here?
Plus.
Because of the sigma.
Right.
Good. So that's plus. As a plus goes here because this is a sigma. Now, which term did we split off?
The n plus 1.
The n plus 1.
So it goes
1.
2 times I.
So,
2 times n plus 1 minus 1.
yes, and we can do the textual substitution in our head, right? So 2 times n plus 1 minus 1. Now, does everybody see how we did the split off term?
Sure.
Are we good?
We're going to have to use split off term like every time pretty much. Huh?
Pretty much.
Yeah. Oh, big thing.
Okay?
Yeah.
But now, what's jumping out at us? Equals by the what? No. Equals by the inductive hypothesis. Are you with me? Oh, yeah. Because we said we're going to prove this assuming this, right? Because we're assuming the conjuncts of the antecedent, right? Because we're proving an implication, yeah? So what does our inductive hypothesis say this is?
N squared.
N squared. Are you with me? So this equals n squared plus 2 n plus 1 minus 1. Now what is it? Now let's look back up here. What is it that we're trying to prove? We were trying to prove that we're trying to get this to this side, right? Well, what can we do here?
Math.
Equals by some math. Okay, so let's do some math. So let's multiply this out. What do we get? N squared plus 2n plus 2 minus 1 is 1, right? Are we good? But this equals by, what are we trying to get it to?
Factoring
Equals by, yeah, let's factor.
and the full square.
We can just say math.
Yeah.
Math, factor, whatever. So what is this?
N plus 1.
N plus 1 quantity squared. Boom, we're done.
That's the proof.
And now do you realize what we did? We didn't have to do an infinite number of cases.
And there were no axioms.
Well, actually, we are using the mathematical induction axioms. Okay? In fact, the mathematical induction axioms are what let us do this.
Can you explain that?
Yes, we are going to explain those in detail. But now, do you understand now how to do, what was your homework assignment for today? It was to prove what? Your mathematical induction problem.
That is for n greater than or equal to 0.
N greater than or equal to, so now what's the base case going to be in this one? Yeah, it was for n greater than or equal to 0. And what was it? The sum, was it a sum?
Yeah.
What was it?
1 less than or equal to I less than or equal to n.
One less than or equal to I less than or equal to n.
Body.
Body I.
Equals n times,
N times n plus 1 over 2?
yeah.
That's how you add all the numbers.
Yeah. That's 1 plus 2 plus 3 plus dot 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 plus n. But what this is, what you're proving is that 1 plus 2 plus 3 plus dot 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 plus n is 1/2 n times n plus 1. Right? This is what you're proving. This is also a really important one.
That's Gauss.
Gauss proved this when he was, yeah.
Who's that?
You have not heard of Friedrich Gauss, one of the most famous mathematicians of all time.
Gaussian elimination.
Yeah, same Gauss, mathematician, Gaussian elimination. Also same electromagnetic Gauss's law, electric field.
Yeah, I wouldn't know that. Electric field.
Physics. You should know physics. We live in a physical world. Because we live in a physical world. And those are the laws that we obey.
I live in a spiritual world.
You live in a spiritual world? Well, maybe we live in both. Who knows? What's the connection between the physical and the spiritual? Whatever. Okay. Okay, so now how are you going to prove this? How are you going to prove this? By mathematical induction. What's the base case going to be?
0.
Oh, good question. This is a little bit different from what we did, because how are you going to do 0? What is this when if n is 0? It's false. What happens if you have false in the range? What rule do you use?
That thing.
How did that work? Come on, what happens if you have false in the range? If any quantification, what happens if you have false in the range of any quantification? What rule do you use? No. Starts with an E.
Empty range.
The empty range rule. Well, is that the identity for addition? Are you with me? It has to be the identity. Uh-huh.
Can we do it?
Yeah, you want to take a little time to do it?
Yeah, you can do it on the board, bro.
No, I'm not going to do it on the board for you. That's your problem. But do you see how to do it? Okay, maybe why don't we take 5 minutes out Why don't we slice 5 minutes out of this, starting from now, okay? And I'll let you guys work on it.
Wait, what was that proof?
Hmm?
What was that?
Oh, it was,
We can write it down on our slide.
no, it's not going to be on the slides. It's a homework problem.
Like splash screen proof.
Oh,
You know what I'm talking about? It's sum on I range 1.
it's sum on I range 1 less than or equal to I less than or equal to n, I
Well, that is,
1/2 n.
equals 1/2 n times n plus 1. Okay? So prove. And this is for all, but wait, there's more to it. It's
N is greater than or equal to 0.
for all n greater than or equal to 0. And because they told us n greater than or equal to 0, the base case is 0.
What do we say that 1 less than or equal to I less than or equal to 0 is false?
Equals by math, false. So there should be some sort of a math computation at this point, you know, when you do this. You need to, oh, I should not have erased that. About how that pans out. So, yeah. I'm sorry I erased that. Do you guys need this? Did you have it in your notes? You should have it in your notes, right?
You have to carry these here. Because you forgot to drop this down. You forgot to drop down your zero.
oh, I just started with this. Yeah. But it doesn't equal 0.
Okay.
Oh, it's 0 times, yeah. Oops. So I just have to prove that this, I'm just getting this to be 0.
You know what? Why don't we just go ahead and end it, yeah.
Yeah.
I'll go through these proofs tomorrow. I'll go through these proofs tomorrow.
You want to do sign off?
Yeah, shall we do a sign off? Are we still recording?
Yeah, we haven't stopped.
Oh, okay.
Wait, is it right? Say,
Oh, hold on, let me just do this one sign off. Okay, see you tomorrow. Okay, now.
that was awesome.
I need more than that.
Oh, you need more than that?
Take two.
Okay, all right. Okay, then I'll answer your question. What's your question?
Is that the right way to use empty range? So
It's
False?
false equals by empty range rule. Yes, yes,
it.
yes.
cool.
Yeah, I can't have a 3-second.
Okay.
That's not
All right. Are you ready for this? Okay, now I'm going to do the real sign off.
Okay.
Okay, so what we'll do tomorrow is we will take a look at the mathematical induction axiom and prove these theorems and show how the theory relates to the practice that we're just doing now. So, see you tomorrow.